Hi, everyone. My name is Michelle Pesca, and I work on the marketing team here at Flatiron School. I know we had some folks slowly trickling in, but I did want to just introduce myself as I'll be leading today's webinar and helping our presenter out. We're super excited to be able to offer today's workshop, which is titled The Science Behind Netflix Recommendations. In a few minutes, I will intro Ben Oren, who is a coach at our Flatiron Chicago campus and also our presenter for today's material. First, I did want to point out that there is a Q&A and a chat feature in this webinar. We encourage everyone to drop any questions that you have throughout the workshop, and then we will reserve a few minutes at the end to answer them. So to practice, why doesn't everyone type into the Q&A box what city that they're joining us from? And with that, I will pass it off to Ben.
Great. Thanks, Michelle. I appreciate you setting this up and making introductions here. So if you didn't know, this webinar is about the science of Netflix recommendations. First, we'll just do welcome and just general introductions. So welcome. If we can get some interactive elements of this thing going, I think that'd be best. So there are two elements here. First, there'll be a Google Doc. They'll be dropped in the chat later on. And afterwards, there's a GitHub that contains more information about recommendation systems in general, and also a code along that you can do either through a Jupyter notebook or just by clicking a link that'll actually go through code that'll let you code a recommendation system example. Both of these services do require accounts, even though they're free. So if you'd like to log in or sign up for these and get a hold of the interactive features here, that'd be great. So thanks. Before we jump in here a little bit about who I am, my name is Ben Oren, and I graduated from the University of Chicago. I bounced around the legal and health tech fields for a while, doing various data sciencey things. And now I'm a coach at the Chicago campus of Flatiron School teaching data science. Michelle, I'd really like to get to know the people who are attending here. So if you could drop the Google Doc into the chat, and everyone, if you'd like to take advantage of the interactive features here, go ahead and introduce yourself, maybe give your name, a quick blurb about you and your background. And if you'd like a LinkedIn, a Git link, a Twitter link, or some other way to get in touch and keep the conversation going. This is broadly organized around a Flatiron School data science lecture that is given in the fourth module. The Flatiron curriculum is organized around 4 modules of content, with the 5th week being a 3-week-long capstone project that students take on their own. This isn't a full explanation of the topics that are given on recommendation systems in Flatiron, but it's enough to give you a little gloss about how recommendation systems are used, what mechanisms go into calculating them, and a little bit about remote learning, which in this world we find ourselves in, we've all had to adapt to. So if this is your first interaction with remote learning, welcome, and I hope you find it tolerable. So let's dive right in here. Let's talk about recommendation systems in general. So the question that brought everyone here is, how does Netflix make recommendations, right? A large part of being a data scientist is breaking things down into smaller constituent parts and thinking through problems so that they can be questioned with data or answered with data. So thinking like a data scientist, the question, how does Netflix make recommendations, starts with, why make recommendations at all? This is part of the broader data science process. This has various names, one of which might be the data cycle, one of which might be CIM, which stands for the Cross-Industry Standard Process of Data Management. That's the specific process of data analysis that is gone through at Flatiron. You'll notice that everything begins with the business understanding, right? We have to investigate the world to come up with specific questions to ask of our data, to ask that we can answer with data analysis. From there, we go into understanding the data, preparing the data, doing some type of modeling, some type of evaluation. From that step, we can go back to our business understanding to see if we have indeed answered the question we set out to. You'll notice that there are lots of arrows going back to the business understanding step. This is something that has to be kept in mind at each stage of analysis to me, making sure that each of the decisions that you're making in your data analysis process are leading toward answering that question. The way that you clean data, the way that you extract data, the way that you choose your models all have implications for how the business question you're answering is answered. And so you have to keep this in mind at each step of the data analysis process. So with that in mind, what is the business understanding of making recommendations? I think the best way to answer that is with a silly GIF. So especially in, again, the world we find ourselves in, we're having a lot of time spent in front of our devices. We're consuming a lot of video content, right? Businesses are delivering this content and they're focusing on a couple things in general, right? One is how to just start user engagement. Like how does a business attract users in general to their service? Secondly is how do you increase user engagement? Once someone has started using your service, how do you keep them using your service and increase use of that? And finally, how do you help the users discover new content? Once people are using your service regularly, how do you keep a steady stream of content flowing for them to engage with? All of these questions are answered partially by building recommendation systems, building systems that give content to specific users based on mathematical calculations. So with that in mind, let's start the process here by having you recommend me movies. So if you had to recommend a movie for me to watch after this event, what would you recommend? Go ahead and if you're following along on the interactive doc, go ahead and drop your answer to that in that document. I'll take this opportunity for people writing to take a sip of my ludicrously orange water here. So let's see. Oh, we have a lot of engagement here. We have James from Atlanta. We have Erica from DC. Stephen from Brooklyn. Shulia from Denver. Cool. Some recommendations we have going here. Shawshank Redemption. That's a tremendous movie. I've seen it about 300 times on TNT and basic cable, right? Orange is the New Black for my ludicrously orange water. Great. Ozark. I've seen a tremendous number of ads for Ozark. A tremendous amount of people talking about it. I haven't actually seen it. And I actually just saw Parasite for the first time a few weeks ago. It is indeed dope. So cool. Please keep dropping names, bios, and ways to get in touch if you'd like to do so in that doc while we're speaking here. But the process of a recommendation system, or the process of recommending something, isn't quite obvious, right? So when you think of making a recommendation to something, of something to someone, how do you make that recommendation, right? Do you think of stuff that's currently hot, like Ozark? Do you think of classics like Shawshank Redemption? Do you think of things you've heard are good, like orange is the new black? It's hard to pick criteria for how to make recommendations, right? This is called the cold start problem. Making recommendations, you don't have any information about the user. You have a little bit of context for me. I'm kind of dorky. I drink silly water drinks. But other than that, you don't really know what kind of content I'd like, right? So there are a couple of possible solutions to this problem, the cold start problem. The first is to just make generic recommendations, suggest what's popular or suggest what's trending. The second possible solution to the cold start problem is to force the user to provide data. So forcing the user to sign up with a social media account that provides a wealth of sociographic data that can be used to calculate how they would like any given thing, right? Another way is for requiring answering questions when a user signs up. So answering questions either about the types of things they might like or the types of generic genres they might enjoy. There are a lot of different ways to calculate what questions to answer, and we'll talk about those a little bit in the later on in the presentation. Making the solutions to the cold start problem, generic recommendations and providing data, generally break along the lines of the two sides of what's called the long tail graph. This is a graph of any given item's popularity, and there's a general relationship that we find when graphing this. Across any system that recommends or that has items that people can engage with, we find that the popularity of a couple given items is off the charts. So a few items have a massive amount of popularity here, right? So this is like the Tiger King region. So draw a little Tiger King with a little crown for the area of the graph representing enormously popular items. But that's a very small number of the total number of items, right? Very, very quickly, as we descend down the popularity graph, we get down into what's called the long tail here. This is the vast majority of items that have a very relatively small popularity, but this is where the money is made for a content delivery system. These items are usually cheaper to acquire, cheaper to produce, and they tend to stick around longer. They also provide a lot of value for people who like niche content. If someone is looking for a genre of French New Wave movies, they're going to pay a premium for a service that can provide them that, if that's the only service that they can find to provide them, right? So we have a bit of a trade-off here where the popularity of something isn't necessarily related to how profitable it is. And we want to be able to recommend specific parts of this long tail to specific users as a business, in the business context of our problem, right? So how do we do that? How do we go about recommending things? So there are different types of population engine or recommendation engines as I erase the Tiger King. Broadly, we ask a couple of questions. The first question we ask is, will our recommendation engine incorporate non-aggregate data? If it doesn't, then we're going to build what's called a non-personalized engine. I thought I turned Slack notifications off. This is a recommendation engine built out of non-personalized information. This recommends content that is aggregated according to popularity, according to what's trending, any broad aggregated characteristics that don't depend on any information from the items or the users themselves. The splash pages, the first pages that a user sees when they're first engaging with a content delivery system, are usually these types of pages, or type of recommendation engine. The pros of this is that it's really easy. You just grab the most popular items from a list, which is very easy to calculate, and you throw them up on the screen, right? That cheap computation is a huge factor in the cost of doing any type of business computer problem. A large component of a data science problem is figuring out how cheaply you're able to solve it. Another pro of a non-personalization engine is that it solves the cold start problem, right? You don't need to know anything about a user before recommending something. The cons here is that it's not personalized. The recommendations aren't personalized to any given user. You're recommending the same thing to everybody, right? A less obvious con is that new items can't get traction. If more popular things are recommended, the same items are going to be recommended over and over again. They're going to get more engagement. They're going to keep remaining popular. And it's harder for new items to break through into that dynamic, right? So a lot of, once the user information and item information is available, a lot of recommendation engines incorporate it. Once non-aggregate data is incorporated, then we ask another question. What type of data is incorporated? If we can incorporate data about the items themselves, the things being recommended, then we create what's called a content-based recommendation engine. These content systems are based on making recommendations about an item's features. The data for that might look something like this. So the rows in this data table are just the individual items, here movies, right? And the columns are the specific characteristics of each movie. In data science, these are referred to as features or independent variables. So as an example of that, a feature for some movies might be strictly quantitative, like a Rotten Tomatoes score, the number of times that items been viewed, its IMDb rating, or the year it was made, right? But it also might include more qualitative variables, things like who the director was, who the main actor was, what genre the movie is in. And it might also include tags that are created by the company themselves. For example, was this movie critically acclaimed? It's not obvious what it means to make a movie critically acclaimed. Is it number of Oscars? Is it number of Oscar nominations? Is it percentage of reviews that mention the word good in it, right? Similarly, we might ask if a given movie is a classic. So is it fall into the category of Shawshank Redemption, Gone with the Wind, Citizen Kane, movies of that nature? Again, it's really hard to determine or draw lines around what a classic is. And so there's a lot of judgment that goes into creating this tagging system that creates this feature set. Once this data set is calculated for every item, then this basic process is undergone. So this is kind of a broad step-by-step overview of how to build a content-based recommendation system. First, we collect all our data and perform exploratory data analysis, or EDA. This is exploring basic relationships in our data set that help guide our later analysis. We might ask how many movies in a given genre there are, what the correlation among genre and director are, etc., helping us determine relationships in our data that we can make further later decisions on. Then we calculate a similarity metric for each pairwise item. For each item in our database, we create a metric for how similar that item is across the entire feature set. We can think of this as finding the distance between each of the items in multidimensional space. So in the graph on the right, imagine that our feature set only has two variables in it. And we want to find the distance between item one, or the similarity between item one and item two. We would calculate that similarity by finding the distance between item one and item two. Here, we're calculating the distance by cosine similarity. that is taking the angle of the cosine of the angle between the two items and saying that's how close they are. That has certain properties that are desirable for recommendation systems that we can talk about later in the chat if you'd like. Notice that this requires a certain assumption on the part of our analysis. We're assuming that the similarity of items in multidimensional space tracks the similarity of actually experiencing that item. So if we have two items that are close together at multidimensional space, the assumption is that the actual experience of viewing those two movies is more similar than the experience of viewing two movies that are farther apart in multidimensional space. So that assumption might not necessarily hold, and it's an assumption that's based on the individual features in our data set. So when we're constructing these things, data scientists have to combine a lot of different skills. They have to be part psychologist by being able to interpret what the specific experiences of these different features are. They have to be part business person by working through the business concepts of these problems. They have to do a lot of data analysis and statistical work. And there's also a lot of computer knowledge that goes into manipulating the types of tools that can handle these large data sets. And so combining all of the different skills are a necessary part of kind of any data science project from soup to nuts. After finding the similarity metrics for our items, for any given item, we rank the rest of the item set by how similar or how close the rest of the items are. So if we want to find the closest movie to Shawshank Redemption, we rank the rest of the set of movies by our distance or similarity metric. Then we recommend the top n of that sorted set. So if we were Netflix and we want to make sure that we want to recommend the top 10 movies to Shawshank Redemption, we would find the top 10 similar movies to Shawshank Redemption based on that similarity metric. Other similarity metrics that are often used in this context besides cosine distance are things called Jacquard distance, which is based on the analysis of sets, and a Pearson correlation, which is what people often refer to in common parlance as things being correlated, right? So after going through that sequence of steps, we've built a machine that can produce an arbitrary ranking of items for any other given item in our set. What are the pros and cons of this constant system approach? Well, first, you can perform calculations immediately, right? It solves the cold start problem. There isn't user information based on this that requires it to work, right? It's also easy. It's easy to calculate. It's also easy to perform. And we also provides recommendations for unique tastes, right? It gets a little bit at the long tail problem. But there are cons to that kind of degrade its ability to reach into the long tail. First is that it requires robust tagging, like the sets of features in our example, like genre, whether it's a classic or not, etc., requires a manual tagging system for people to specifically match movies to genre, movies to whether it's a classic or not. This takes a lot of time. This takes a lot of money, and so it's not as effective as some other systems on those bases. Another con for using a content system is that it tends to over specialize in specific types of items. When the commerce part of the internet was first getting going, this was a common way to make fun of it, was that you buy one mop and then for the next 6 months, anything was recommended to you was other different types of mops. I'm not a huge mop guy myself. I don't really see how people can buy more than one mop. And so that doesn't seem like the best type of system, right? So another way to incorporate data that incorporates user data is a collect recommendation system. This incorporates user preferences about each item in the data set. So when we're talking about recommending movies, we're usually talking about rating the movies from a 1 to 5 basis scale, right? The problem with this is that just most users don't have a lot of ratings, right? Like, I don't think I've rated myself anything on Netflix, even though I've seen my fair share of things on Netflix, right? So Netflix trying to use ratings to offer a recommendation for me isn't going to work if they're just looking at data I've provided, right? So the solution to that is to find different relationships among users and use that information to calculate ratings. In much the same way that similarities were found among items in our content-based system, similarities are found among users in a collaborative system, and the ratings that the users have given across the entirety of the data set are used to calculate ratings for any individual user. This is what the data broadly looks like in a collaborative system context. It's called a utility matrix. It's a listing of the users, usually in row form, and usually the columns or the features are the different movies in the set, and the actual data are the ratings that any given user has made to any given movie. So you can see that in this example data set, I've made a couple of recommendations here. My colleagues at the Chicago Data Science Campus and in the Seattle Data Science Campus, Max, Joelle, Aaron, and Greg have likewise made some ratings on a few movies. But broadly, about half of the movies don't have ratings in them. When a data matrix does not have a lot of relative data across the entirety of its space, it's referred to as a sparse matrix. What we're trying to do is turn these blanks into calculations. So we're trying to figure out or calculate what ratings each user would have for the movies that they haven't rated yet, right? In order to figure that out, I'm going to go through an example right now called modified singular value decomposition. This is a little bit math heavy, just as a warning. I don't want to scare anybody, but the most intricate thing that we're going to do is a pre-calculus derivative that is very, very easy to perform in practice. So I don't want to get anyone scared off. This will provide a little bit of flavor of how machine learning algorithms operate. Broadly, a calculation is made on a given set of data. Operations on that calculation are performed in order to maximize the calculation according to given to some metric. And then that operation is performed over and over and over and over and over and over and over again until we reach the optimum of the metric that we're trying to look at. So as an example of that, we're going to look at a very simple toy data set. The rows here are just different items. The columns are just different users. And the data is just different ratings that these users have given to these individual items. And we're going to try and calculate what user one has given for, or what user one might give to item 3 if they were to rate it, right? So first, we're going to decompose this user item matrix into an item matrix and a user matrix. So this contains the items, this contains the users. You might notice that the columns on the item matrix and the rows on the user matrix aren't filled in. We can talk, it's pretty cool what they actually are, but it's a bit involved. And so we can save that for the Q&A session at the end, if you'd like. So first we take the decomposed matrices and we fill them with ones. We initialize them as a starting point. Then we make calculations as to what the ratings would be from these decomposed matrices. We recompose a matrix based of ones to see what those ratings would be. So here you can see that the ratings are all 2 if the decomposed matrix data is all 1, right? Then we want to compare this reconstituted matrix with our original matrix. We want to get a metric of how similar our reconstituted matrix is to our original matrix. The metric that is common to use is called root mean squared error. All that is looking at the squared difference of each cell. So the squared difference of U1I1 with U1I1 over here, the squared difference of U2I1 over here and U2I1 over here. We add all those together, we take the average of those and then take the square root. That's that number here, right? So currently, this matrix has an RMSE of 1.75 from this matrix. We want to see if we can improve that. The method of doing that is by using gradient descent with alternating least squares. This is kind of like a toy example of how this process goes, but broadly, this is how it works even on larger data sets. There are many more algorithms that can be used to calculate the user item matrix, and this is just one of those ways. So first, we replace one value in the item matrix with an X, a variable, and we see how the calculations change based on that. Our reconstituted matrix has broadly the same 2's as before, but because of the way that matrix multiplication works, the top row is now filled with X plus 1. What we're going to do now is compare this with our original matrix and solve for X to try and minimize the RMSE. We're going to do that through a process called gradient descent. So this is where the math comes in. I'll just flash through this pretty quickly. In order to minimize gradient descent, we're trying to minimize the squared differences of comparing our original matrix to our reconstituted matrix. If we simplify it just with addition and subtraction, it looks like this. If we want to minimize this, we take the derivative of it and we set the derivative to 0. And solving for X, we get 2.5. That was really, really quick. The math is over. It was relatively painless, right? It's essentially a pre-calculus problem that people do in high school. That's about the extent of the kind of calculus that is used in most of the machine learning algorithms. It's about the extent of the calculus that's used at Flatiron, and it's about the extent of the and the kind of matrix multiplication that I demonstrated earlier is about the extent of linear algebra used. So if you were put off by the math, that's kind of all that needs to happen here. And all of that math is gone through in our curriculum. So once we have X is 2.5, once we've solved for that, we can throw that back into our reconstituted matrix. So the item being replaced by 2.5 results in a reconstituted matrix where the top row is now replaced with 3.5s instead of 2s. We can compare that back to our original matrix, and the RMSE is now 1.58. It's dropped from the original RMSE of 1.75, right? So we have a kind of machine here that we've built that can lower the RMSE. So we just crank that machine sequentially. We go through that process over and over and over and over and over again for each individual cell in the item matrix and the user matrix until we find that the RMSE is not decreasing anymore. At that point, we look at our reconstituted matrix and say, okay, this is as good as we're going to get. And these are the values that result from that process. We can compare our final reconstituted matrix here to our original matrix, and we find that the final RMSE is about 1.18. So we are, in general, about 1.18 off from each prediction. That's pretty good for like a toy example. And so we would make our, we would fill in for user 1 for item 3, rating of 3.7. So this is the process of filling in the sparse matrix that we have to deal with based on users not having a lot of ratings in our system. And from this, we can calculate how to recommend which movies. We simply take the movie that has the highest calculated rating and recommend it, right? So what are the pros and cons of this system? The pros are that it's personalized. Like each rating that is calculated for that user for that item, right? So it's a very specific personal system. And also, much more than the other two recommendation engines we looked at previously, is able to recommend niche items in the long tail. So it's able to extract the value from the majority of the item set that companies have access to. The cons of a collaborative systems that we just went through are that it's computationally expensive, right? This process is not easy on the old microchips in our computers, right? And so that takes money and time to be able to do. There's also a slight popularity bias where things that are popular with other users will tend to be recommended more frequently. But there are ways to construct metrics instead of RMSE to optimize for that can mitigate that problem somewhat. The big con of this collaborative system is that it needs ratings to operate, right? There's the cold start problem, and it bites this one hard. If there aren't any user ratings to operate on, no amount of machine learning magic is able to calculate ratings for us, right? So this can only happen once something has been bootstrapped up high enough that user ratings exist in the system, right? So how does Netflix make its recommendations? Well, we have enough context now to be able to answer this question. So Netflix uses a hybrid of content-based and collaborative-based systems. So they manually tag movies with categories, like I demonstrated in the content-based item matrix, things like genre, whether something is a classic, etc. Then, after making those categories and grouping items together, they run a collaborative system. So instead of their utility matrix being users and items, it's users and groupings. And so they're recommending to users more groups of things than individual movies, right? The math under the hood has the benefit of flattening out distinctions between movies. And so more movies are able to be recommended in a closer value to what users are able to actually experience when they look at movies, right? Netflix also incorporates, since they've been running up enough user-specific behavior that is kind of fun to think about. So they have different recommendations for the time of day of any given person and the time of week of any given person. So think through how you watch things on a weekday versus a weekend, right? If it's a weekday and like me, you're just kind of beat after a hard day of teaching students, you want something kind of easy to engage with, maybe something funny, something that doesn't tax you too hard, right? Then over the weekend or when you have time to unwind, you're able to engage with more arty, hard, like more intellectual stuff, right? And so Netflix actually creates different user profiles for people based on the time of day and runs different utility matrices for people based on what time of day they're recommending, what time of week they're making recommendations in. Netflix also has a bunch of fun A/B testing. They test different ways of presenting material to people to see if there are any statistically significant differences in how that presentation results in choices that users make. So, for example, the screen here is almost completely composed of A/B tested facilities. So the thumbnail of any individual movie might be A/B tested. The actual tags of the group that's being offered don't change within the matrix, but these specific words that are on the screen that are shown to the user might change. So instead of critically acclaimed ensemble movies, for another user, they might be recommended this exact same bucket of movies, but the tag might be Oscar-winning group movies or something, right? Also, the order in which these are presented is A/B tested, and the color palette itself of movies is A/B tested. So information like this movie being more green than this movie is included in the content-based system that is created. So they can get pretty crazy with the amount of features that they're able to extract out of any given movie. Get my pointer back instead of the pen. Okay. So let's just summarize what we've gone through tonight. So we've gone through the basics of the data science process, or CRISP-DM. We've gone through a couple of problems that recommendation systems face, like the cold start and the long tail. And we've talked through the three main types of recommendation engine systems that are calculated: non-personalized, content-based, and collaborative-based. We've also talked through a little bit about how a content system process is created and how a model-based SVD operates on a machine learning level. So I hope you've enjoyed walking through all this stuff. If you have, and you want to engage with this stuff more, this is a deep, dark rabbit hole that you can spend months in. So as a kind of introductory portal to that rabbit hole, we've put together some resources at the GitHub link there. And that link should also be emailed to, should also be in the email of the webinar that you received. Thanks, everybody. That's the presentation. I hope you had fun talking through data science a bit. Like, I'm, as referenced, a big dork, and so I really like just talking through any data science aspects. If anybody has questions, you can submit those in the chat function, and we can talk through those for about 15-20 minutes. I do also want to mention that the kernel of this presentation was created by Ish Lim. She was a data science coach at the New York Flatiron campus. And she has written a number of recommendation posts on her blog about recommendation engines. Those posts are linked at the GitHub link that was posted. And please dive down that rabbit hole with her if you're interested. So yeah, with that, I'd like to welcome back Michelle, and we'll go through some questions.
Thanks, Ben. So we do have a few questions in the Q&A box. Let's see. How much data does Netflix collect? Browsing history, for example.
I'm not sure privacy-wise, like how much information about your system Netflix is collecting, but the amount of information that they have access to just through engagement with their platform, just through clicking on clicking through their system and selecting movies to watch is in the terabytes. Like, it's massive. They have tens of millions of users, and they're in operation 24/7 around the globe every day. They're generating huge amounts of data every day. That's partially why the computational expensiveness of these systems comes into play. Setting up a machine for generating recommendations for that size of data set requires an enormous amount of hardware power, electricity, man hours, etc. And so optimizing for the cost of calculating these things is definitely something that Netflix keeps in mind. The Netflix challenge is something that kind of touches on this question. The Netflix challenge was something that was offered in the late aughts by Netflix. They offered a cash prize to data scientists to come up with a recommendation system that could beat their own internal recommendation system. The one that was created, or the one that won, was a version of the modified SVD with alternating least squares gradient descent that we went through. But Netflix ended up not using that because in their own internal business processes, because it was too computationally expensive to implement. They had to alter the calculations at key points in order to make it cost effective. That is a long, rambling answer to how much data they collect, but I thought that that context was fun and useful.
And how does or does Netflix track which device you use to view content?
Most things on the internet do that. That's like a core kind of capability of engaging with the internet, is tracking which device is being used to access the service. So things like Twitter do that, things like Facebook do that. That's kind of like that's been a part of the internet ecosystem for a while. What I'm talking about is purely tracking like the hardware and the OS that is being used. So the Apple iOS, the Android, ice cream or whatever they're on now, right? The various iterations of the desktop operating systems, and like the browsers that are used to do so. Anything else besides that gets into kind of murkier territory, but the both kind of legally and the capabilities of doing so, like there's kind of a constant shifting along that terrain. But in general, sites have been able to see what you are viewing their content on for a while. So that's definitely a part of calculating all these things as like user information. Yeah.
Does Netflix make suggestions based on what I watch or only what I rate? Because I never rate anything.
Yeah, that's part of the problem of having a sparse data matrix, right? And that's part of the problem that we solved when we went through the math of how to calculate ratings through singular value decomposition. We didn't have the rating for that specific item that we calculated, but after going through a process of machine learning, we're able to get a fairly good guess for what that user would rate that item. So that process works even if a specific user has not rated anything, as long as the rest of the users have rated enough of the set of movies, we can generate guesses for what any given user would rate any given movie. The key is just having enough ratings across the entirety of the data set, which the first question mentioned is massive, right? So given the massive amount of data that they have, they're able to make fairly specific recommendations just because the total number of ratings is fairly large, and they're able to use the ratings that they do have to make calculations for people, even if any individual person hasn't used any ratings at all or hasn't made any ratings at all. I'm going to plug in my power cord really quick. Oh, watch me disappear. Yeah.
Okay, Ben, if you can still hear me, does
Yep.
Netflix often just simply ignore personalized data to push their own content? Do they like pay attention to personal data that people put together in their Netflix profiles?
Yeah, I mean, that's definitely a part of the creation of a collaborative system is any sort of user data that is given to them at any point. So data that is collected through a Facebook profile when you sign up, or data that is given through a kind of user profile that is created, or data of any specific user's behavior in the system. So that doesn't only apply to ratings, right? That could be the sequence that you click through when you're looking at what movie to watch. Whether you click really fast or like linger on one specific bucket of recommendations, or whether you select really deeply into one specific bucket of recommendations, all of that data kind of goes into the bucket of data from the user that is used to make recommendations, right? That data is kind of like used in different ways, excuse me. But any piece of data that can be attached to a specific person is ultimately tried out in the process of making recommendations.
I see that Netflix generates a percentage match, such as 98% match for a show. Does the collaborative rating model directly correspond to this percentage rating match?
It can, yeah. So I mentioned that there are different metrics other than root mean squared error that can be used to compare how any given calculated matrix performs on our original data set. Besides root mean squared error, there are a number of different metrics that can be used to calculate a given percentage for what rating is going to be for which item for which user. We can think of the number of items that are above the number 3. So the number of items that the system creates that are 4 or 5, what percentage of those are end up to be accurate when we compare it to our original matrix. There are a bunch of other kind of more complicated algorithms that can spit out probabilities of any given recommendation, like instead of spitting out a matrix of recommendations, what they spit out is a given number for a given recommendation, a given probability that this recommendation is accurate. And so, yeah, they're essentially displaying to you when they do that, the results of a specific collaborative system that was used to make a recommendation.
Okay, unfortunately, we are out of time for questions. I did want to say to everyone that any questions that were unanswered, I will share Ben's contact information that was shown on a previous slide in the follow-up email after this workshop. So you're more than welcome to reach out to Ben, and he's happy to answer any of the additional questions that you have regarding this workshop and his experience as a data scientist and a coach at Flatiron School. Ben, if you don't mind just going to the next slide. And then really quickly, before we log off, I did want to invite everyone to join Flatiron School for our Change Things Challenge. This is a 6-week challenge, which is currently happening, and it's a roadmap to stay inspired, make positive changes, and to connect with others in the tech community. To learn more, we invite you to join us on Facebook and join the Flatiron School Change Things community. And then Ben, if you don't mind switching to the next slide. And then again, thank you so much for joining us today. It's so great that we're still able to offer events, even though they're virtually. We hope that you enjoyed everything that you learned today, whether it was new or whether or not you felt inspired to learn a new skill such as data science. To learn more about Flatiron School and how you can become a data scientist just like Ben, visit us online at www.flatironschool.com. Thanks again, and have a great night, everyone.
Thanks, everybody.